Okay, let's continue with the applications of differentiation. So speed is the magnitude of velocity, and the average speed for a time interval t1, t2 is the distance traveled over the difference in time. So now let's have a look at the average acceleration. And again, we have a time interval t1, t2, and this would be given as the difference in speed, or the difference in velocity over the difference in time. So v2 is the velocity at the time t2, and v1 is the velocity at the time t1. And in the same manner, the instantaneous acceleration, we call that a. A for acceleration is dv over dt. So the first derivative of the velocity, but as the velocity is nothing else than the first derivative of the distance, we have the acceleration being the second derivative of the distance over time. We will have to have a look at the second derivative, or you will have a look at the second derivative and higher derivatives in year 12. So don't get confused by that, but just doing the same thing again and again. Where can we use that now? Have a look at example 17. A particle moves in a straight line so that its position, x in centimeters, relative to the origin 0 or O at a time t in seconds is given by this equation. So x is t cubed minus 6t squared plus 5 for positive t, or t equals 0. We want to find the initial position of that particle, the velocity, the acceleration, and we want to describe its motion. Okay, let's start with the equation. For the position, x is t cubed minus 6t squared plus 5. The first derivative is going to be the velocity, so take the first derivative of this equation, so 3 goes down, left with t squared. 2 goes down, so we know negative 12t. And we said the acceleration is going to be the second derivative, so we take the derivative of the derivative. Okay, so 2 goes down, we're going to get a 6t, and we're left with the 12 as constant factor, as constant term here. So what's happening at t0? So we want to have a look at that. If we substitute 0 in there for the initial equation, we're going to get 5. Okay, good. So if we substitute 0 in there for the velocity, we're going to get 0. There's no constant term, so it's 0. For the acceleration, we're going to substitute t with 0, and we're going to get negative 12. So that's negative acceleration here. Therefore, we can say initially the particle is instantaneously at rest, 5 centimeters to the right of the origin, with an acceleration of negative 12 centimeters per square seconds. Second question is B. Find the times when it's instantaneously at rest and determine its position and acceleration at those times. So we want to be at rest, so we're having a look at the first derivative, and when we say it's 0, we're going to find that the tangent has a gradient of 0, and that's a stationary point, so it's at rest. Good. First derivative, we're taking this down here. Okay, 3t squared minus 12t equals 0. This is factorized, can take out a common factor of 3t, so 3t is 3t times t minus 4 equals 0. So when that is 0, it's only 0 if one factor is 0, so if this is 0, we're going to get an answer, and of course if t is 4, we're going to get the answer 0. So therefore we can say the particle is initially at rest at t0 and stops again after 4 seconds. So there's something happening. And at t0 we know that the position is x5 and the acceleration is negative 12. Now we do the same thing for t4. So we substitute the 4 into the initial equation here, and we are getting negative 27. And we also want to investigate the acceleration. So we substitute 4 in here, and we're going to get 12. Good. So therefore we can say after 4 seconds, the particle's position is 27 centimeters to the left of the origin, and its acceleration is 12 centimeters per square seconds. So what I want you to do now is have a look, read through the other worked examples in the textbook, and then have a go on the exercises.